Lab 2. Motion of a falling object. The purpose of this lab is to observe the motion of an object that is dropped from rest and falls somewhat slowly, straight down. The first step is to capture a video of the motion, then analyze the video in Tracker to extract the object's position with respect to time. Then we will construct a computational model that includes only the effect of gravity. Next, we will construct a computational model that includes both the effect of gravity and the effect of drag. Finally, we will compare our models to our observations. I've taken a video of a crumpled piece of paper falling from rest. I mark the center of mass of the piece of paper as it falls. Here's the data gathered. I will be comparing this data to the data generated by my computational models. Before creating a computational model, let us consider the motion of the paper using Newton's second law. In this case, the initial velocity of the paper is 0. Since the object is falling downward, the final velocity is negative. Since the left side of the equation is negative, the right side must also be negative. Since the mass and the time are positive, that means F net must be negative. We know that close to the surface of the Earth, gravity is a constant force pulling downward. Let us create a computational model that assumes that the only force acting on the paper is gravity. This is a Python program where gravity is the only force acting upon the object. When we run the program, we see the object falling straight down in the y direction. We take the information generated by the program and enter it into a spreadsheet, along with the information that was gathered through Tracker. When we graph the two sets of data, we can see that there is a big discrepancy between the observed motion and the motion of the model. In order to construct a better model, we must consider forces other than gravity that are acting on our system. One such force is air resistance, or drag force. For our second computational model, we will be using the formula for turbulent drag. This formula indicates that the drag force is proportional to the square of the velocity and is in the opposite direction of the velocity. This Python program models a falling object with both a gravitational force and a drag force acting on it. The yellow arrow indicates the gravitational force downward. The blue arrow shows that the drag force is in the opposite direction of the ball's velocity. Initially, the drag force is very small, but as the ball's velocity increases, the drag force also increases. When we add the information from our second model to the spreadsheet and graph it, we can see that the second model much more closely predicts the motion of the falling paper. There is still a small difference between the two curves. This could have been caused by several factors. For example, there might have been video distortion, or perhaps the center of mass was not precisely marked in each frame. Overall, the model that considered both gravity and drag was able to closely predict the motion of the falling paper. What does it mean? What do these computational models tell us about the motion of a falling object? Let us look at the first model, where the only force considered was the force of gravity. If the only force is gravity, F net will always be negative, and so the object's velocity will keep increasing in the negative y direction. However, if the object is subject to gravity and drag, since drag increases with velocity, eventually the drag force will equal the force of gravity. At that point, F net will equal 0 and the velocity of the object will become constant. This final constant velocity of motion is called a terminal velocity. We can demonstrate this using our second computational model. Here I've increased the length of time that the model will run in order to allow it to reach terminal velocity. As you can see, the arrow indicating drag increases until it is equal to the arrow indicating gravity. I've entered the values generated by the program into this spreadsheet. The first column shows time, and the second column shows velocity. If you look closely, you can see that the velocity is increasing. However, if you keep scrolling down, you will reach a point where the velocity will stop increasing and remain constant. This is the terminal velocity. What if, instead of starting from rest, the object was initially thrown downward? If an object is thrown downward and is traveling at a speed greater than terminal velocity, it will slow down until it reaches terminal velocity. Here I've modified the Python program to show an object that has been thrown down and is traveling at greater than terminal velocity. Initially, the slope of the graph showing position versus time is quite steep, indicating a high velocity. As time passes, the slope decreases until it is equal to the terminal velocity.